Okay, so let's get started. All right, so I hope you all had a good exam. How was the exam from your perspective? Easy, hard? Hard, very hard. Okay. What about anybody else had any other opinion? Long, okay. Logical, okay, that's good. So it's not illogical. All right. So we will start grading it tomorrow. We'll try to get some feedback back soon. All right. My TS thought it was easy. I thought it was moderately hard, not hard. Okay, but we'll see who was right. But the TA felt it was an easy exam. Anyway, so keep in mind that there is a lab due, okay, on April 1st. So you don't have much time between now and the lab. So focus on getting the lab done. Okay, the lab has as much, if not more, credit than the exam. So keep that in mind. Okay, if you have any questions about the lab, we are here. Office hours have restarted after spring break. So come and ask questions. Okay. All right. Any questions before I start about the lab or anything else? People have started on the lab, right? Okay. It's time you should have at least started, otherwise you will have issues finishing. All right. Okay, good. So let's start today. We have two problems to discuss in distributed systems. One I already introduced last time. We talked a little bit about it. I will reintroduce it and then do a quick recap and then continue. That's on leader election. Okay. And the second one is called mutual exclusion. This is where we see how to do distributed locks. Okay. How do you take the concept of a lock, which you probably have seen when you have multi-threaded programs, and try to make it distributed. Okay. Okay. So just as a recap, we started this last time. What is the leader election problem? Essentially, when you have a set of processes in a distributed systems and they want to choose a coordinator directly for some task. Okay, how do they themselves decide who the coordinator process is? The coordinator in this case will be called the leader. What the coordinator does is not as important. Okay, because the coordinator could be, essentially the master server and the clock synchronization algorithm, or it could be a super peer in a peer-to-peer system. Okay, so the role of why you are choosing the leader is not as important here, but how to choose the leader is what we are going to discuss. Okay, so in some sense, it doesn't matter which of the processes get chosen as the leader. You just need one leader. Okay, and the idea is either when the system starts, you start off the leader election algorithm, you pick a coordinator, that coordinator then takes over the role of whatever they're doing. Or if the current coordinator fails, then you can restart the leader election algorithm to pick a new leader. Okay, so in either of these cases, you have to essentially run this algorithm. And last time I talked about the bully algorithm. I'm going to speak about that very quickly here. Okay, and then we'll talk about the next one, which is the ring algorithm. So here is the basic idea. So in the bully algorithm, what we want to do is we'll assume that processes are ordered from 0 through n. Okay, and you want to pick the highest ID process that is still alive as your coordinator. That's the rule. Okay, now this is just an arbitrary rule. You don't have to say I have to pick the highest ID process. You could have said I can pick the least loaded process as the coordinator, or I can pick the node with the most amount of CPU resources as the coordinator. The criteria for how you choose the coordinator can keep changing. Okay? Here we pick a very simple criteria, which is we order the nodes, pick the highest ordered node, highest ID node as the coordinator. Okay? And the basic idea is any process can start the election algorithm. Okay? So in this example that you see here, process number 4 has started the election algorithm. And the way you start an election algorithm is you assume you know the IDs and the IP addresses of all the processes in the system. Okay, so 4 is going to send now a message to 5, 6, and 7, okay, saying let's start an election. Okay, 7 was the old coordinator, is gone down. Okay, that's why there's an X there. Okay, so it will not get the message. Its message will not reach it, but it will get to 5 and 6. Okay, and then when you receive an election algorithm, or let's start an election message from one of your lower ID nodes, you basically just send back an OK message to that node saying we got the election algorithm. Okay, and the OK message serves as an I am alive message to a lower ID process. So you know that that process knows that there's at least one higher ID process that is alive, and someone else is going to win the election, not it, because it knows that there's somebody who has a higher ID than itself. So one of those nodes is going to win. So it's going to drop out. Okay? So essentially 5 and 6 send OK messages to 4. 4 drops out of the election, and then this process is going to recurse. Okay? 5 will start an election, 6 will start an election. So what's going to happen is you see your 5 started an election by sending a message to 6 and 7. You see that 6 also started an election by sending a message to 7. Of course, that message to 7 doesn't get to it. And then when 6 gets a request from 5, it's going to send an OK to 5, which causes 5 to drop out. Okay, when you get an OK, that tells you that there's a higher ID process, so you drop out of the election. So now 6 is the only one left. Right? So 6 is going to declare itself the winner and say, I am the new coordinator, and send out this. Okay? So that's basically a very quick recap of Bully algorithm. Multiple elections can be in progress at the same time. Each election can have an election ID with it so that you know what you're responding to. So if 4 had started an election and 3 had started an election, this whole process would continue. And in both cases, 6 would be the one that would win because it is still the highest ID process. Okay? That doesn't change the fact that multiple elections can start. That's okay. You will end up with the same end result, at least in this case. Okay? If 7 comes back up, 7 is crashed, it comes back up, it can see that it has a higher ID process than 6, which is the current coordinator. It can start an election. It will win immediately because there's no other higher ID process, and it can declare itself the coordinator and take back the coordinator role if it wants to. Okay, is this clear? Very simple election algorithm. Okay, I'm going to talk about another one, and then we'll compare the two. Okay, this one is called a ring-based election algorithm. Okay, same concept. Okay, as there are processes in the system, they want to elect a coordinator. We'll assume all processes have unique IDs. Okay, and in this case, we'll assume they are arranged in a logical ring. Okay, so each process only needs to know its neighbors. Okay, in the previous one, each process needed to know the ID of all other processes, so you could send back messages. Here, you only need to know your left neighbor and the right neighbor in the ring. Okay, and here is basically how you are going to make it work. So any process can start an election. Here, you see that same concept as previously. Okay, now you are in a logical ring. 5 has started an election, and 2 also started an election independently because both 5 and 2 saw that the coordinator had crashed. Okay, so what happens in this case is you basically, to start an election, you put your ID onto a message and you send it to your neighbor. The neighbor appends its ID and sends it to a neighbor, and this message is going to circulate to the ring and come back to whoever started the election, and the IDs of every process that has received that message and forwarded it to his neighbor is now back in that message. Okay? Then you just look at all the IDs in the process and you pick the highest ID process in that message as the new reader. Okay? So here you will see that 5 sent a message saying I am 5 to 6. Okay? 6 is going to append its ID to the message, so there will be 5 and 6. It's going to try to contact 7. 7 is dead, so it can't do that. So it will then contact the next neighbor, which is 0. We'll send it to 0. 0 is appended to ID, so you have 5, 6, 0. That's going to circulate to the ring and come back to 5. Okay? And 5 has all of the IDs. You'll see that 6 is the highest ID process. So it will send 6 has won the election as another message that will circulate through the ring. Okay? And you see at the same time, 2 started a different election. Okay? That message is also circulating. So you'll see that 2 has appended its ID, came to 3, 3 appended its ID, then it's come to 4, and that will continue to circulate. Okay? And it will make a full circle and come back to 2, and 2 will see again all the process IDs that are alive, and it will also choose 6. So both of those elections are going to give you the same end result. right? Is this clear? What we are trying to do. So essentially, we are querying processes. In one case, we queried higher ID processes. Here, we are using a ring logical link topology to query nodes to see who is up and who is not, and then we pick one that has the highest ID. Is this clear? Okay, question there. In any leader election algorithm, any ID, any node can start an election. Yep. Yes. Okay, so there's a question here about what happens. So let me rephrase the question so it's clear what is actually being asked. So what happens if in the middle of a leader election algorithm in progress, some node either crashes or some other node comes back up? Okay, so the leader election algorithms give you stable results only if the node structure is stable while the election is in progress. Okay, you could have asked your question by saying this leader election technique is choosing 6, but before you declare 6 as the leader, what if 6 also crashes? Then again, your leader election has failed. And in your case, you said 7 came up, and maybe 7 gets chosen, maybe it doesn't get chosen. What happens, right? So if you have dynamics in the midst of an election, you are not going to get a stable result. Then you may have to restart the election, and that's okay. You can restart, and eventually you will converge. Okay, so the idea here is you will get a good result only if the nodes that are participating are stable, that no new nodes are coming up or no new nodes are crashing. Then you have stable result. Otherwise, you may not get the right result. You might have to restart or something. Okay, question. Okay, what happens if the ring is so large it's not feasible to get a stable result? Then we have a problem because if you have nodes going up or down, you will not get a result that is stable. The only right answer to that question is maybe you need hierarchies in that, because you have to have smaller groups that are stable and they can have their own leader, and then you have to have some decentralized technique. You don't have to have one coordinator in that case. Because in the peer-to-peer system, that's exactly what might happen. So there are lots of dynamics in P2P systems. So you had super peers that only control a smaller group, not the entire network. So that's still okay. But if you try to do it for the whole network in P2P, you would actually have that issue. Okay? Yes. Okay. Question is, if this is a ring-based approach, the processes will have the nodes of the next ID. In this case, you see that if the node has crashed, you need to know your neighbor's neighbor also, right? So technically, you can't just get away by saying I only can know my immediate left and right neighbors, okay? Because if one or both of them crash, then I don't know who else to communicate to. The ring has to still continue to function if some node has failed, right? So when there are failures, you need to know your neighbor's neighbor and things of that sort. Okay? So you could do that by essentially sending a message in the other direction and probing who was your neighbor's neighbor or something. So you could have said, I am 7's neighbor. I need to know who was 7's neighbor and send the message the other way and find out. Or you can keep multiple, like you can say, I keep my neighbor's IDs, I keep my neighbor's ID, I keep my neighbor's ID, because 2 nodes can fail at the same time. So you have to keep some more information for this to function. If you strictly keep only 7, you won't know that there is 0 is the next one to send to in this case, right? So that you have to deal with. Any other questions? Okay. So let's just do a very quick analysis of this, both of these, bully and ring. So you will see the ring complexity is 2n-1 messages. Okay, because in this case, one node has failed. So each circulate, once you circulate to the ring, you send n messages, and you declare the result, then another message circulates. Okay, so that's 2n-1 messages. Okay, that's the complexity of the ring algorithm. The bully one is a little more complex. That depends on who started the election. Okay, if the lowest order node started an election, you have order n square messages. So you send n-1 messages and you recurse, then you have n-2 in the next election and so on and so forth. So you'll basically get order n square. That's n-1 plus n-2 plus n-3 all the way to 1. Okay? In the best case, the highest order process starts the election, it immediately wins, and it sends n-2 messages to everyone else saying, I am the new leader. Okay? So you will be somewhere in between those two, depending on who has actually started the election. But the general complexity is order n square. Okay? So you will see that one is linear, the other one is quadratic in complexity. Is that clear? Okay. All right. So let's now, so that's leader election. We'll now talk about a different problem, which is distributed synchronization. Okay, this is basically a problem of making a lock distributed. Okay, we know how to do locking. Right? You did this for threads programming and so on. Let's take a case where you need the lock itself to be distributed. How do you actually deal with that problem? Okay, so for single processes, you can use semaphores, locks, monitors. The distributed system processes may be running on multiple machines. So you can't keep the lock state with one process. The other process may not know what the lock state is. So you need a mechanism for making this work in a distributed environment. And we'll see multiple approaches. One that uses a coordinator to coordinate the lock. That's a simple approach. And then we'll see more decentralized and distributed approaches for keeping locks and see how they all work. All right. So here is a very simple example. This is kind of more like a lab example to know why you might need a distributed lock. You have multiple clients that are going to, let's say, an online store, making buy requests or checking the current state of the catalog and so on. And since multiple of them are making requests at similar times, there may be race conditions that may cause the stock amount of items in stock to change dynamically and so on. And if you don't use locks to do this, you will have some race conditions and bad things. Okay? And in case of your lab, you got away by just putting the lock on the server side. You didn't have to worry about it. Okay? You just put locks there, and that was fine. That's a fine approach. But in some cases, you can't just do that. You might have to have the lock actually be distributed across multiple processes, because if the client, let's say client sends a request, the server holds the lock, and then the client dies and then does not do anything subsequent to release that lock, then your lock is going to be stuck forever. So you have all these problems in a distributed environment that you have to deal with. Okay? This is why the concept of a lock in a distributed setting is actually quite complicated, as we will see. All right. So let's start with the simple case of how can you make a lock work in a distributed setting. So we will essentially use a coordinator, which means it's really a centralized approach. Okay? In which, so what we'll assume is all processes are numbered. Okay? And we'll assume that the processes in the system will first choose a coordinator for the lock. Okay? And we know how to do that. We'll just run a leader election, and then we'll pick a coordinator. So some process is now the coordinator. Okay? Now, the goal here is every process has to now check with the coordinator before it can enter the critical section. The coordinator is holding the lock. So you are basically going to send your lock request to the coordinator. And when the coordinator says the lock is granted, then you know you have the lock and you can get into the critical section. And then to release the lock, you will send another release message to the coordinator. Coordinator will set the lock to be free. Okay? So essentially now you are sending lock requests, getting back replies, sending lock release requests, getting back replies, and so on. Okay? And there's a coordinator process that's going to handle this for every lock in the system. Okay? So to get the lock, you basically send a lock request, wait for a reply. The lock is in use, you will block. Okay? This because there won't be a reply. This is the same thing where you try to do a lock acquire. The lock is already in use, you are blocked until whoever is holding the lock will release the lock. Same will be true here. You'll send a request and you will not get a response. You will just be blocked waiting for that request. Okay, so here's a very simple example. There are 4 processes, 0, 1, 2, and 3. Okay? We have chosen 3 as our coordinator. Okay? So, and then the 3 is going to essentially keep the state of the lock, which is basically a binary variable that says is the lock free or in use. And it will keep a queue of all the processes that are waiting for the lock. Okay? So initially, one sent a request for the lock. Okay? Lock is free, so one basically got the lock. So you sent an OK 1 saying you have the lock. So 1 is now holding the lock, it's in some critical section, and then 2 has now sent a request for the lock. Okay? Since the lock is in use, 2 cannot get the lock anymore, so you'll just put 2 in the queue. You will not send a reply. Okay? That's why 2 is going to be blocked, because this is a blocking call, and you'll just wait. Okay? Eventually 1 is going to release the lock. Okay? At that point, 3 is going to check the queue to see if there is any process with the lock. There is 1, and it will grant the lock to 2. Okay? Then 2 enters the critical section and so on. Okay? So that's a very simple approach. Okay? But you can imagine that there will be lots of problems when things crash and fail. Okay? So you could say 1 got the lock and then 1 crashed. Okay? 2 is waiting for the lock, but the lock is never going to be released because the process that holds the lock is gone. Okay? So you can't actually do anything. Or worse, coordinator crashes. Okay? So now essentially it's granted the lock and it crashed, so the other processes may not know what to do in this case because they can't even make lock. Okay? So failures of processes can cause all sorts of problems. Okay? That's why this is a complicated issue. We'll talk a little bit about this. Any questions on the basic approach, how this works? Yes, your question. Okay, that's a good question. Question is, when 2 has made a request and has not gotten a response from the coordinator, how do you know if the request was lost or the coordinator lock is in use? That is why you are not gotten it. Okay? So for the purposes of this example, assume that messages are going over TCP. Okay? And TCP will not worry about, so once you use TCP, you don't need to worry about lost messages because TCP will take care of retransmissions for you. Okay? So you can essentially think of the TCP ACK as at least I got an acknowledgement saying my message was received. So I know that. So lack of a reply from 3 in this case means that the lock is in use, not that my message was. Okay? If you did not use TCP, that would be a valid question. Then you have to modify the protocol to send an acknowledgement saying I got your message. That's not an OK message saying you can have the lock, but you have to add an ACK saying I at least received the message, and you will hear back at a later. Okay? So that would have to be modified, but here we are just assuming a reliable network, which means that TCP is going to take care of this for us. We won't worry about it. Is this clear? Any other questions? All right. So what are some pros and cons here? So one advantage of the approach is because you're keeping a first come, first serve queue. Okay? It's a fair process to allocate locks. Locks are simply granted in the order in which they are received, that is in first come, first serve, or FIFO order. So you're not giving lock preferentially to any one process. Okay? It's a simple technique in terms of its complexity. There are only 3 messages we are using here: a request message to get the lock, a grant message that gives you the lock, and a release message to release the lock. Okay? So those are some good things about the approach. The shortcomings, there are many. Okay? Single point of failure, the centralized approach. Okay? Coordinator crashes, the whole thing is going to go down. You can't distinguish between a lock and use from a failed coordinator. Okay? If a client process that holds the lock crashes, then the lock, you are going to have a deadlock situation because no one can make progress because the lock is never going to be released. Okay? So you can have deadlocks, you might have a failed coordinator, all kinds of problems. Okay? So there are things you can have to do to figure out how to do this. I'm not going to go into approaches to solve a problem, but I can give you a couple of ideas to think about. So if the coordinator crashes, you can basically have leader election that can essentially elect a new coordinator, and that can take over the lock management. Okay? However, the new leader has to actually recover the current state of the lock. It doesn't know what is the current state. Is the lock in use? Are there queues? Was there a queue of processes waiting for the lock and so on? Okay? So the state of the lock, okay, that the coordinator maintains, which is the state of this queue, as well as the variable that says if the lock is used or not, has to be also kept somewhere on disk, okay, in a file. So that if the coordinator crashes, the new coordinator can go and read the file to see what was the state of the lock. Otherwise, the new coordinator doesn't know how to start, okay, because it doesn't know what was happening before the coordinator went down. So you have to add all of these things to that. By itself doesn't solve all the problems, but those are some ideas that you can think of for how to deal with failures in the system. Client failures is a much bigger problem. A coordinator is up, client that holds the lock goes down. Okay, now you cannot actually figure out what to do because you're deadlocked. That problem is not solved yet, because that's much harder to deal with. Okay, the only way you deal with that problem is you have to fundamentally change the semantics of the lock. Okay, you can't say current semantics as once a lock is acquired, whoever holds the lock can hold it indefinitely for any arbitrary amount of time before they release the lock. We do not put any limits on how long you can hold the lock. Okay, only way to deal with failed client processes is that you have to actually put a timer on the lock. Okay, and you can have a lock for the next t time units. Okay, and if the client is not done by that time, it has to actually renew the lock with the coordinator. So the coordinator knows that the lock is still required. Okay, then in this case, if the client fails and the lock expires, the lock actually comes back to the coordinator. But that fundamentally changes the semantics of what locks mean, because you want to make sure that you can hold the lock for an entire critical section, even if it's a long critical section. Okay? So you have to change things to make things work in presence of failures. Okay? That's the short answer. But anyway, we won't go too much into these details, but it's something to keep in mind. Okay? Yes, question. Question is, that's a good question. What happens if the coordinator crashes while it is writing to disk? So that's a really good question. So you want to make sure that you actually first write to disk and then send the lock grant request to the process. Okay, but you could ask that same question: what happens if I wrote to disk, but the coordinator crashed before the grant request went out? Right. So you can deal with all this when we get to distributed transactions. So that's basically very similar problem in databases. You are trying to make a transaction. You want to make sure no matter where you fail, things work. So when we get to distributed transaction next time, we will try to solve some of this problem. So essentially, you need atomicity for writing to the file and granting the lock. And we don't know how to do atomicity yet. Those two operations have to be done together or none at all. Right? So that's called atomic operation. We'll talk about that next time when we do transactions. Okay, but it's a good question. All right, decentralized algorithm. So we'll say we don't like centralized. Let's use decentralized technique. So here we are going to use the concept of voting. Okay, we'll assume that there are n replicas and there's a coordinator for each replica. Okay, so think of each replica or each process as a thread that is simply doing lock management. Okay, so to acquire the lock, you need a majority vote, okay, which means that you need a strict majority of the coordinator to say okay or not. Okay, so essentially non-blocking. So the coordinators, the majority of them say yes, you have the lock, then you can go ahead. So what's happening now is the lock state is replicated on multiple nodes. Okay, so now there are multiple coordinators that are all replicators. They all have the same state. So you basically have to get okay from a majority. You don't need to wait for everyone to reply because they all have the same state. Internally, they have to keep the state consistent. We didn't say how to do that, but so long as the state is consistent, so long as the majority of the nodes say yes, you can have the lock, you can say this is safe for me to get. So that's the general process. Okay, you can have again coordinator crashes. Okay, we won't actually talk about that here. Okay, there are some analysis that you have to go through to know what's the probability things can go wrong and so on. But let's just skip that for a second. Okay, but just assume that you take this centralized approach. Okay, and the way you decentralize it is you made multiple coordinates. Okay, each coordinator keeps the exact same state of the lock, and so now you have to send your lock request to multiple coordinators and wait for a strict majority to grant you the lock, and then you are good. Okay, so even if some coordinators fail, so long as the majority of the coordinators are up, the lock can continue to function. That's the basic idea. You never want a minority to make the decision for you, but you still want a strict majority. Okay, so that's a decentralized. That's one decentralized technique. I'll talk about another one, which is actually a little more interesting. This one is called Rickert and Agarwala's locking algorithm. Okay. This is going to use the notion of logical clocks and timestamps, okay, to do this. So essentially, we are going to use event ordering. Okay. We talked about logical clocks. We saw how that gives us event ordering. We're going to use event ordering and total order. Okay. And here's how you are going to do it. If a process, n processes again. Okay. Process K wants to enter the critical section. Okay. It keeps a logical clock, okay, like any other clock. That's an integer. Okay. It's going to increment the clock. So that's your timestamp. You increment the clock by 1, and it's going to send a request lock message saying, I'm process K. My logical clock value is whatever it sent here. Okay, the timestamp value. Okay, and it has to wait for a reply message from all other processes. Every other process in the system has to tell it go ahead. Okay, before you can go. So essentially, you're asking for the lock. You send your timestamp, ask for the lock, then you wait for a reply from everyone before you can go ahead. Okay, and then how does a process send back reply? So what's going to happen is if you receive a request message from some other process, okay, if you don't need the lock, there's no contention locally, okay, you will send a reply. Okay, you send reply saying, I don't need the lock, go ahead. Reply just means go ahead. Okay, if you are already in the critical section, that means you hold the lock in across all the machines in the system, you will queue the request because you cannot reply yet, go ahead, because you hold the lock. Okay, okay. And the third case is you are actually also contending for the lock, because you also want the lock and this other process. Meaning you have yourself sent request messages. So in this case, you are going to compare logical timestamps. Okay, and you will say who sent the request first based on the logical timestamp, and whoever sent the request first based on logical timestamp wins. So if the other process has a lower timestamp, that means it sent the request before you did in logical timestamp order, not in real clock time order. And you have to yield the lock. You have to send a reply saying, okay, you get the lock first and I'll get it later. On the other hand, if your timestamp is lower, you win. Okay? You win across these pairs. Maybe there are others contending. You may not win globally, but you will at least win against this process. In this case, you are going to queue and say, let's wait before you get to enter the critical system. So the logical timestamps here is essentially giving us an ordering of all the processes that are contending, and the timestamp is what tells us in what order they should enter the critical section. If there is contention, if you're the only process trying to enter, everybody is going to send replies and you're done. There's nothing to worry about. Okay? But if multiple processes are trying to enter the critical section at the same time, the one with the lower timestamp wins. Okay? It gets to go first, and then the other process gets to go. Is this clear? It's called Rickert and Agarwala's algorithm. You can see the complexity is 2n minus 1 because you're sending requests, you're getting back replies from everyone. Okay? So essentially, that's how it's going to work. Okay? It's fully distributed. Right? So there's no coordinator of any sort. In some sense, every process has to be participating in the lock management in this case. Yes, question. Okay, good question. Question is how do you deal with what happens when the process crashes? How do you deal with it? Okay, so that's what we have on the next slide. So there are pros and cons. Properties, good properties is fully decentralized. No need for a coordinator, no centralization, etc. Downside is endpoints of failure. Okay? As was asked, if any process crashes in this system, okay, you're not getting a reply message from that process. Okay? And what did we say? You need a reply message from every other process before you can enter the critical section. So even if there is no lock contention at all, nobody wants the lock. One process simply crashed. Okay? You are asking all processes, should I get the lock? That process is not going to reply. Everyone else is going to say, go ahead. That one process is not going to reply to you. You cannot make progress. That's the definition of what the lock protocol does. Okay? So essentially, dealing with failures is a big problem in this approach. Okay? It is fully decentralized, okay? But since all processes are involved in a decision, any one process crashes, you are stuck. Okay? So this is one of those cases where a decentralized or a distributed technique actually has worse failure property than the centralized technique. Okay? And at least in the centralized process, if some arbitrary process crashed that had nothing to do with lock management, you could make progress because coordinator is up, you are up, you get the lock. Here, if some arbitrary process that is not involved in the lock crashes, you cannot make progress. Okay? So counter example of distributed system may not always give you better failure properties than centralized approaches. By and large, they do, but in this protocol, you actually have worse properties. Okay? So yeah, it doesn't work with failures, unfortunately, which is something you do want, but it doesn't work. Is this clear? Yes, question. So this was actually designed without assuming any failure. So it's a good approach in that you don't need a coordinator, you don't need any clock synchronization, because the other way to do fair allocation is to timestamp requests and say who made the request first, that process gets to go. You don't need to do all that. You're riding on Lamport's clocks, event ordering to figure things out. So a lot of good things, but doesn't have failure resiliency property. So many techniques don't do any failure recovery. So if you don't need that, you can use it. If you assume that it has to work in the presence of failures, you should not use this. Is this clear? Okay. All right. Yet another technique, okay? Token ring algorithm. Okay, this is like another ring-based approach. Okay, so let me give you a little bit of background of where this algorithm came. This is also a distributed locking technique. Okay? This technique actually came from networking. Okay? So I think maybe 30, 40 years ago, when local area networks were first being designed, there are two competing technologies. There's Ethernet and there's token ring. Okay? So when you bought a PC in those days, you had to actually decide based on which environment the PC was going to connect to, whether you wanted to get an Ethernet card or a token ring card, because they're not compatible. Right? So either companies had a token ring based local area network where you connect your network to you connect a machine to the network, or that Ethernet. As you can imagine, Ethernet 1, that's what you have now. Token ring just faded away, but it was a good technique in its day. Okay? And what did the token ring do? Okay? So essentially, it assumed that all the nodes in the network were numbered 0 through n. Okay? So here's our network. Okay? It's just a flat network. Those are all the circles are actual machines that are connected to a network. Think of a network as just a long wire. They're just connected to each other on a long wire. Okay? So you can send message to anyone. Okay? Now, the goal of a local area network is to ensure that only one process can transmit a packet at any given time. Okay? Because if two processes try to transmit to two different packets at the same time, you are going to have what is called a collision. Because essentially you try to put two packets, they go over the network, they collide, and then the packet gets garbled. Okay? Same thing is true of wireless channels, by the way. In today's Wi-Fi world, because you have one access point, you cannot actually have two machines send packets at the same time to that access point on the same frequency, because you will essentially collide. So only one machine can transmit at any given time. Okay? So you have to think about this as a big locking problem, because you have to essentially have a lock on the network, and then you can transmit. That guarantees that nobody else transmits. Okay? So the token ring algorithm had a built-in locking protocol. Okay? So what they did is they created a special packet called a token packet. Okay? And this token circulated through the network. Okay? So it's basically, this is where the ring comes in. So this just looks like a set of machines with numbers on them. But if you assume that 0 can only talk to 1 and 1 can talk to 2 and 2 can talk to 3, you will see that the way the communication occurs in the network is a ring fashion. Because regardless, although 0 can actually talk to any node, we restrict 0 from only talking to its right neighbor. Okay? So essentially, if you want to communicate to some machine, okay, so if 0 wants to send a message to 4, you can't directly send it to 4. You have to send it to 1, 1 sends it to 2, and so on, and it gets to 4. Okay? So essentially, you constructed a logical ring out of this network. Okay? So in this network, you have a special packet called a token packet, and the token is going to keep circulating. And the rule of the network is you cannot transmit any packet until you hold the token. The token is essentially your lock. Okay? So you don't ask for a lock, you just wait. Okay? Token keeps circulating and eventually gets to you. Once it gets to you, you hold the lock. So whatever messages you wanted to send, you send out. Once you're done, then you send the token to the next machine. Okay? That's the general rule. Okay? So this token keeps circulating, and essentially whenever you have the token, you just get to transmit. Until you do, if you don't have the token, you don't transmit. Okay? Now in the networking world, because you don't want to have arbitrary delays for sending your packets, you can hold the token for a max amount of time. Let's say you say 10 milliseconds. Okay? So essentially the locking time is at most 10 milliseconds. Once you get the token, you're 10 milliseconds to send whatever you want, and then at the end of the 10 millisecond, you have to forward the token even if you have more data, and you wait for it. It's like time slicing, exactly like time slice. You get a time slice when you hold the token. When the time slice expires, you have to send the token to the next machine. Is this clear, what I'm saying? Okay. So that was essentially a token ring protocol. Okay. You can use the same idea now for locks. Okay. So essentially now your token is the lock. So if you have to grab the lock, you don't actually ask for the lock. You just wait for the token to come to you. We will just relax the assumption that you have to hold the token for a fixed amount of time, because when you are writing a program, you cannot assume that your critical section will always be less than 10 milliseconds. Maybe it's going to take longer. So we will not put that restriction. Okay. So once you have the token, you can wait for as long as you want to finish your critical section. Then you pass the token to the next element. And then if they don't need the lock, they'll just pass it on. But if they need the lock, they'll hold it, they'll do their critical section, and they'll send it on. Okay. Very simple idea. Is this clear? Okay. Yes. It is very much like a round robin. It's good. Okay. That's a good question. What is the need for a token? Okay. So the reason you need a token is that you don't know that every process actually needs to enter the critical section. If it was true round robin, you just give 10 milliseconds to every node. Okay. And then, so in this case, every 80 milliseconds or so, you will get to enter the critical section. But that wastes time if some node does not want to enter the critical section, right? Yeah. So the message that skips is the token. That is the message. So the token is essentially that. So if you want to skip, you just say, here, I pass the token. So that's exactly what it is, right? So that's what they did. Okay. Now the problem here is what happens if the token is lost, right? Because network can go down. There can be either the network can lose the token, or the machine that holds the token can crash. Then what do we do? Okay. Once the token is gone, it's not going to start circulating again. You'll be waiting forever. Okay. So this is basically where the problem arises, right? So tokens can get lost because this is not, you are not assuming the network is perfect. Okay. There could be errors in transmission, or the machine that holds the token can crash. In the networking world, this was easy. Okay. Because you had a bound on the time each node could hold the token. You said you can hold it for at most 10 milliseconds. You are guaranteed that if that time was t, and there are n nodes in the system, you should see the token at most every n times t time units. Okay? If the token doesn't appear after n time t, you know it's lost. So that's the only way it won't appear, because you have bounded the time you hold the token. Okay? So in the networking world, that was not a problem, because you just have a timer. If the timer goes off, then you basically say that somebody has to regenerate the token and start passing it on again because it's lost. Okay? So you can just elect a coordinator and say you keep a clock. If every n times t time units the token doesn't appear, you generate a new token and you restart the ring algorithm, and everything is good. Okay? So, and you can only have one node regenerate the token, because if you can imagine, if every node just says, I haven't seen the token ever since I sent it last, and regenerate will be 2 tokens or more than 1 tokens, then you have a problem. Okay? But we know how to do leader elections. We have a leader that's doing token regeneration. Okay? So that part is solved. Okay? But in our case, where we are actually using it as a real lock, we cannot do this, because we have assumed you can hold the lock for an arbitrary amount of time. So you don't know if the token is lost, or if there is some node that's really having a long critical section and is taking its own time. Okay? So you cannot regenerate the token by putting any amount of timer, because we didn't bound the critical section. Okay? So we took up the networking idea works well, except in token regeneration, because you don't know how to regenerate it well. Right? You could still put some bound, but that bound could always be exceeded by the excessively large critical second. So there's never a guarantee. The networking world, there was a guarantee, and you needed that guarantee because you can only have one machine transmit at the same time. If more than one machine transmit, you have what's called a packet collision, and the packets don't reach their destination. Yes, question. Yeah. So you could have, as is being mentioned, you can have other approaches where the node that's holding the token for an excessively long time can send additional messages saying, I'm alive, I'm holding the token, so you know you don't need to regen. So you can do all kinds of things, but you have to add more of that for this to work. If you just wait for the token, it doesn't show up, you don't know what's happening. Okay? But in networking case, you knew what was happening because you knew the token was lost after the threshold amount passes. Is this clear? Okay. Very simple idea, but failures you got to be careful how to deal with. All right, so let's do a very quick comparison, and then we'll see what other things we want to discuss. Okay, so we have looked at centralized, decentralized, distributed, token ring. Okay, first let's look at all the problems. None of this actually really give us a good solution. But distributed locking is inherently a hard problem. Okay, not very easy to deal with. Okay, centralized approach, coordinator can crash. Okay, decentralized approach suffers from starvation. Somebody is holding the token for a very long time. Distributed approach, crash of any process takes the whole system down. Okay, token ring, you can have a lost token or crash processes. So this will tell you that is not an easy thing to solve, regardless of how you deal with it. Okay, and then they have different amounts of complexity and different amount of time delay it might take for you to essentially figure out how much time it's going to take to get the lock and so on. I'm just going to talk about this one just so that you know. Centralized case, there were 3 messages. You basically ask for a lock, you get a lock, you release the lock. Decentralized was 3 MK because you have multiple requests being sent, responses being sent back, and so on. Distributed 2n-1. You send requests, you get back all replies, you are done. Okay. Token ring depends on the length of the ring. Okay, so you can have a very large ring that can have very large complexity. If it's small, it's less. Okay, so different trade-offs, different amounts of, or not different amount, but different types of problems you have to deal with. Okay, any questions on this? All right. So one thing I'm going to do, and then we'll end it a bit early today, is to talk about an actual large locks service, just to give you some sense of how these things are dealt with in very large scale distributed system. Right? This is called the Chubby lock service. This was this locking protocol that Google developed for some of their distributed system. Okay, so you will see how it essentially is. So this is designed not for fine-grained locking, but very coarse-grained locking. And it's going to use file systems to implement locks. Okay? So you have this concept of a Chubby cell, okay, which is essentially a set of 5 machines that are coordinators for locking. And these machines support up to around 10,000 servers that might need all kinds of lock. So this is essentially the locking service. So if you need a lock, you go to Chubby, you ask for the lock, and when you get the lock, you can do whatever you want, and then you can release the lock. So it looks a little bit like the centralized approach, except that you will see that there are 5 coordinators per 1,000, 10,000 servers. And so, okay, one of the 5 machines is actually kept outside the data center. It's kept in a different location, so that if even the entire data center goes down, okay, the state of the lock is kept somewhere else. That was the file I was talking about, right? So you have all the 5 machines keep the state of every lock, they keep it consistent, but one of the machines is just outside for handling large-scale disasters. You will still have consistent state of the lock, right? And we are going to essentially use file system, like the files are the mechanism you are going to keep the state of the lock. Okay? So what are some use cases? You can essentially use it to do leader election. Okay? This is essentially the opposite. You're using locks to do leader election. Okay? How do you do this? You have a lock. Okay? N processes content for the lock. Whoever gets the lock is the leader. Right? So you can essentially use locks to do leader election. You can just contend and somebody wins, only one node is going to win, because the lock guarantees that only one node has the lock. Okay? And then you can advertise yourself as the. Okay? You can also use it for many other cases where you can hold locks for hours and days if you're doing some large scale computations and so on. Okay? So here is essentially a picture that shows you how all of this works. So first thing is, within a Chubby cell, you are going to elect a primary node. Okay? And then those are going to have replicas. Each of them are going to maintain a database that keeps the state of the lock. And Chubby manages lots of locks. It should be clear, you're not managing one lock. You're not going to have 5 machine do. So you may be managing thousands of locks for all kinds of processes. So this is your centralized locking service. Every time you want to create a lock, you go to Chubby, create a new lock, and then use it, and so on. Okay? So you are going to use files as the way to do locks. And basically, most file systems internally support locking. Okay? So if you use your local file system, it actually supports read-write locks. Okay? So you can open a file in read mode, read lock mode, or write lock mode, so that ensures that a thread can only have only one writer can go at one time, and so on. Okay? So we'll just use the file system abstraction to keep a state of the lock. For every lock you want to maintain in the system, we'll create a file. Okay? You want to create a lock named foo, we'll create a file named foo. Okay? And then if requests come to ask, there are requests to ask for that lock, we'll essentially start a thread and we'll say, go grab a lock on that file. If the thread gets a lock on the file, we'll grant that lock back to whoever asked. If the lock is in use, that thread will block. Okay? And then whoever asks for the lock has to block. So we are essentially using basic file system locking, okay, to keep state of the lock. And you are using file system locking as opposed to keeping a variable named foo in memory. You could have implemented an in-memory lock. And you could have made a variable and said, every time somebody wants a lock, you try to ask for a lock on that variable and only grant it. But remember that this has to be persistent. Okay? So if you keep things in memory and the machine fails, then all the state is gone, which is why you keep things on disk. Okay? So that keeps things persistent. So here the primary can fail. You can create new replicas and whatnot. Since everything is stored on a distributed file system, okay, all the state is still there even if machines fail. Okay? And you will see that the client, to get a lock, essentially it uses an RPC. So it's going to send an RPC to a Chubby cell asking for a lock. So all the lock requests, lock release, they go as RPC messages. So these are your coordinator nodes. Okay? So this is basically a very simple, not very simple, a very complex version of our centralized locking protocol, except that there are 5 coordinators. They're all keeping state consistent. They're using disk state to reflect the lock state, and so on and so on. Okay? So essentially, this is how Google implemented its locking protocol. Okay, I'm going